we prove this result. And applying our previous result, that is lower sum and upper sum are bounded by the lower bound and upper bound multiplied the volume of the rectangle I. Okay, but we apply this result to our subrectangle J, applying to the case I to be J, and the corresponding partition is the partition determined by the P prime, the definement partition P prime for J. Okay, then we obtain the here the MJF is the is a lower bound of F over the subrectangle J, and multiplying the volume of J will not greater than the lower bound of F with respect to the partition P prime of the rectangle J. And okay, and the lower bound will not greater than upper bound. For upper bound, similar to the previous argument, this can be bounded by the supplement of F over J multiplying the volume of J. So we have this inequality. Now we sum this for every rectangle J from the partition P, we have this inequality. Then we sum the inequality over all J from P. Sum over all J from P. The right hand side is the LFP, the lower sum of F with respect to P. And this term, for every J, you sum up over J, sum for J over P, will give you LFP prime. Okay, this is precisely what we just proved. That is LFP prime is the sum of LFP prime J sum over all J from P. Okay, using this result here, you sum for J over P, give you LFP prime. So this proved the first inequality, and the other inequality are similar. Okay, so this is an important lemma, which tells us if you refining a partition, the lower sum will increase and the upper sum will decrease. Okay, so how about different partition? If we given two partitions, they have none of them is a refinement of the other. Okay, so what's the relation between their lower sum, upper sum? So to solve this problem, we introduce the concept of common refinement. Suppose we have two partitions, P1 and P2. P1 is not a refinement of P2. P2 is also not a refinement of P1. Okay, so suppose P1 is P1 alpha, suppose P1 is P11 cross P1n. Here P1 alpha, P2 alpha, for alpha equal 1 and 2, and the Pn alpha are partition of the edges of I. P1 alpha is the partition of I1. I is the rectangle. It has n components. Okay, so its first edge is I1. So P1 alpha is the partition of I1. Of course, P alpha is 1, 2. So P11, P12 are all partition of the first edge of I, that is I1. And so this determines the two partition of the rectangle I. Okay, so we take for every we take the union of P1I and P2I. So P1I is the partition of the I's edge of I with respect to the first the partition P1, and similarly P2I. So we take the union of their points. So the Pi is also a partition of the I's edge of the rectangle I. Okay. Can I solve your picture? So here in this picture, the black dot is the black dot determined partition of the rectangle. The red dots also determined partition of the rectangle. So the sub-rectangle for the partition P1 is the rectangle with the black edge here, and the partition, the rectangle which is respect to P2, that is the red dots, are the rectangles with the blue edges. Okay, so our P1. So for example, the P11, that is for the first component of the first partition. P11 is the horizontal 5 black dots, and the P21, that is the first component of the second partition P2, is the red dots. Of course, you need to make it a partition, you need to add the endpoints of the interval. Therefore, P21 is actually this point and this two red points between, and also the right endpoints. Okay. Similarly for the horizontal direction. Okay. So the P1, our P1 here, our P1 introduced here. Here I is 1. For the case small I is 1. Is the union of the P11 and the P21. That is all the points, no matter black or red. All these 1, 2, 3, 4, 5, 6, 7. All these 7 points is our P1 here. Our P1 here. For small I equal to 1. Okay, and for the vertical direction, this is also the case. 1, 2, 3, 4, 5, 6. All these 6 points are determine the partition P2 here. This P1 and P2 are the partition of the this edge and this edge, and then they determine the partition of the rectangle. Okay, determine the partition of the rectangle. This partition is the close P1 close P2 in 2-dimensional case. Of course, for n-dimensional, you denote P1 close P2 close Pn, and this partition we denoted by P1 wedge P2. This symbol wedge similar to union, but it is not actually it is not a union. Okay, so we use this new notation. So this partition. This partition, what's this partition? For our picture here, as I said before, the rectangle of P1 is the rectangles with black edges. Okay, and the rectangles of P2 are the rectangles with blue edges. Okay, and so for the P1 wedge P2, for this partition, what's the sub-rectangle of this partition? This partition, for this partition, the sub-rectangle is all the sub-rectangle here, all the small rectangle here, which edge blue or red or black. Okay, so altogether we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So we have 30 sub-rectangle here. All these 30 sub-rectangle are the rectangle determined by this partition of the rectangle I. And for our P1, how many rectangle? For our P1, we just have 1, 2, 3. P1 has 12 rectangle. We counted before. And for P2 is the rectangle which is blue edge. Therefore 1, 2, 3, 4, 5, 6, 7, 8, 9. For P2 we have 9 rectangles. For P1 we have 12. But for our new partition introduced in this constructed in this way, denoted by P1 wedge P2, we have 30 rectangle in our this picture. Okay, so this is the how to this is an idea or a method, a typical method to construct new partition from old ones. That is, given two partition P1 and P2, for every edge you take the union of all the pointers to give a new partition of that age. So for every age, for the n ages, you determine the partition. This determine a partition of the whole rectangle. Okay, so this rectangle is a refinement of P1 and P2. We have two partition P1 and P2. In this way, we construct a new partition, which is a refinement of P1. It is also a refinement of P2. Therefore, this is called the common refinement of P1 and P2. Okay. So we have proved that if you refine a partition, the lower sum will increase and the upper sum will decrease. So since P1 wedge P2 is a refinement of P1, you see that the lower sum with respect to P1 will not greater than the lower sum with respect to the common refinement, and the lower sum is always not greater than the upper sum. Therefore, we have this inequality. Then for upper sum, you in defining partition will decrease the upper sum. Therefore, this inequality is also true. So this is improvement result of our previous lemma. Our previous lemma tell us that for the same partition, the lower sum is always not greater than upper sum. Okay. Of course, this is a direct consequence of the definition of lower sum and upper sum. For the same partition, lower sum always not greater than upper sum. Okay, but this argument tells us that even for different partition, lower sum will not greater than upper sum, because for the lower sum with respect to P1 will not greater than upper sum with respect to another partition P2. Okay. So for our later convenience, we use this Pi to denote all the partitions of P of I. That is, if a P is an element of Pi, this means the P is a partition of the rectangle I. Okay. Now, using this result, we can give our definition of upper integral and the lower integral. Suppose f is a bounded function defined over the rectangle I. Then, for every partition P, we compute the lower sum of f with respect to P. Then we get a real number. Okay. Then all this real number, we consider the supplement of this real number. This is a bounded set of real number because our f is bounded. Therefore, this lower sum will not less than the lower bound of f multiply the volume of the rectangle I, and this will not greater than the upper bound of f over I multiplying the volume of I. So this for every partition P, you compute the lower sum. This is a bounded subset of real numbers. So it has a supplement. This supplement is denoted by this integral, which a minus sign here. This is called the lower integral of f. So every bounded function has a lower integral, which is obtained or computed in this way. Similarly, we consider the infiniment of upper sum. That is the upper integral of f over I. Okay. So this is lower and upper integral of a function over the rectangle I. Now, for a partition P1 of the rectangle I, and we have this result. This is the so this is the definition of lower integral. And if given any P1, this supplement will not greater than the will not greater than the upper sum with respect to the P1. Okay, because for every partition P, the lower sum will not greater than the upper sum which leads back to P1. Therefore, the supplement will also not greater than this, because this upper sum is upper bound, while the supplement is the largest. The supplement is the least upper bound. Okay, so least upper bound will not greater than a given upper bound. So we have this inequality. Okay, this is because L of P, for every P, L of P will not greater than U of P1. So after taking supplement, the inequality remains true. Okay, but this P1 is any partition of the rectangle P. Therefore, we can take the infiniment of this both sides of this inequality, which is back to P1. When P1 runs through the partition of the rectangle I, the infiniment of the right hand side is the upper integral. So we conclude that lower integral will never greater than upper integral. Okay. So so this is the relation between the lower integral and the upper integral. Lower integral will not greater than upper integral. So if they are equal, we say that the function f is integrable over the rectangle I, and the common value of the lower and the upper integral is called the integral of f over I, and use the usual notation without the minus sign or upper or positive sign. Okay, so and we also use the Ri to denote all the integrable functions over the rectangle I. All the integrable functions over rectangle I is a set of functions. This set is denoted by Ri. Okay.